So we're going to start Chapter 2, Section 1. This is actually the second part of this video on finding square roots and comparing real numbers. This second part mainly deals with some definitions that you need to become familiar with. Some of them you may already have a pretty good understanding of. Some of them might be a little new to you. So the first thing we're going to talk about is whole numbers. Whole numbers are 0, 1, 2, 3, etc. So you're counting numbers, but also including 0. Integers is another term you'll hear. So this is all your whole numbers, but then also includes the negative values as well, continuing in the other direction. Something else we're going to talk about in this section is the difference between rational and irrational numbers. Irrational numbers oftentimes arise when we take the square root of whole numbers that are not perfect squares. So yesterday we did discuss perfect squares, such as 4. When you take the square root of 4, you get 2. Or the number 36, when you take the square root of 36, you get 6. But anytime you take the square root of a number, a whole number, other than a perfect square, you get irrational numbers. So let's talk about irrational numbers first. One way to talk about them is that they are numbers that can't be written as a quotient of two integers. Remember, quotient means division. So essentially, irrational numbers cannot be written as a fraction in which you can divide one integer by another. Another way you might think of it, which might be a little easier, is thinking of it as a decimal. So irrational numbers, if they're written as decimals, they neither terminate or end, nor do they repeat with any particular pattern. There's really no rhyme or reason to the continuation of the decimal. So for example, if I were to take the square root of 945, and you can go ahead and put that in your calculator, you'll find you're going to get this decimal that continues without any rhyme or reason, 30.74085, and then it continues from there. Another popular one that many people are familiar with is pi. If you just hit pi and enter into your calculator, you're going to find that it equals approximately 3.1415926. And again, that number also repeats with no rhyme or reason. So those are irrational numbers. On the other hand, rational numbers, these can be written as a quotient of two integers. So you can write them as a fraction, in which case you're dividing one integer by another. As decimals, they either terminate, so they end at some point, or they might repeat forever, but they do so with some sort of pattern. So for example, 3/4. Again, it can be written as a quotient. You're dividing one integer by another. And as a decimal, it terminates, 0.75. -1/3 is another example. As a decimal, it does repeat, but it does so with a particular pattern, -0.333, and that 3 repeats, so we indicate that with the line drawn above. Now, all of these numbers, and all the numbers that we'll talk about in this class, are what we call real numbers. Real numbers, which is basically the set of all rational and irrational numbers. Pretty much any point on the number line, no matter where it is a real number. Okay? So let's apply these definitions to some example problems. So example 1, let's just classify some numbers. I'm going to create a table. I'm going to be giving you some numbers. We're going to determine whether or not it's a real number, if it's rational or irrational, if it's considered an integer, and whether or not it fits into the category of whole numbers. So I'm just going to create this table here. And let's start with square root of 24. Now, if you put the square root of 24 into your calculator, you're going to find that I'll write it down here, it is going to give you 4.89879,486, yada, yada, yada. So it just continues to repeat without any kind of rhyme or reason, just randomly. Is it a real number? Yes. All numbers that we're going to talk about that you can think of, if you can put this on the number line, yes, it's a real number. Rational? No. Remember, if the decimal repeats with no rhyme or reason, then it's irrational. It is not an integer, nor is it a whole number. Next one we're going to look at is 100. The square root of 100, which is 10. Again, real number, yes, you can put it on the number line, it's real. Rational, yes. 10 is not irrational. It is an integer. Okay, remember, integers include all your counting numbers as well as negatives. 10 is one of your counting numbers. And then finally, yes, it's a whole number as well. And let's take a look at one more. Negative square root of 81. So that's going to be -9. Yes, it is real. It's rational, meaning it's not irrational. It is an integer. However, it is not a whole number. Whole numbers only include positive numbers. There's actually a nice table in your book at the top of page 75 that shows you a Venn diagram or a display of how rational, irrational integers and whole numbers can kind of be thought of. Let's look at one more example. In this example, we're going to practice ordering numbers, and specifically we're going to order these numbers from least to greatest. Now the numbers I'm going to give you here, some are fractions, some are decimals, and others are written using radical signs. So my advice to you would be, in these types of problems, just get them all into the same form. So I'm going to recommend that we put all of these numbers in decimal form. This way we can easily see where they lie on the number line and compare which ones are smaller and larger. So 4/3 as a decimal is going to be 1.3 repeating. Negative radical 5 is going to be an irrational number. It's -2.236 continued. Radical 13 is 3.605, and then that continues with no particular rhyme or reason. -2.5 is already a decimal. I'll just rewrite it here. And then finally, radical 9 is just 3. So I'm going to place these numbers on the number line to get a better idea of exactly where they lie. So 1.3 repeating is going to be approximately here. And remember, this 1.3 repeating is the fraction 4/3. That was the original number given. -2.236 is going to be about right here, not quite halfway between 2 and 3, a little closer to 2. And remember, this represented the original value of negative radical 5. 3.605 is going to be down here somewhere, and again, that represented originally radical 13. 2.5 is, oh wait, that's supposed to be -2.5. So not there. Back down here, -2.5. Now this is halfway between negative 2 and 3. So it's going to be to the left of this value. So this dot here represents negative 2.5, and then finally 3, which originally was given as radical 9. So in order from least to greatest, the original numbers that we were given could be written the following way. Negative 2.5, followed by negative radical 5, 4/3, radical 9, and finally the square root of 13.